Welcome. In this session, we are going to continue our look at general rules of differentiation. We are looking at the chain rule. This tells us how to differentiate a composition of two functions. Stated in function notation, it says that the derivative of f composed g at x is f prime of g of x times g prime of x. This looks a bit opaque, and it's a lot easier to understand if we use the Leibniz notation. So, let u be g of x and y be f of u. So y is a function of u and u is a function of x. Then the rule says that dy over dx equals dy over du times du over dx. Of course, when we do this, dy over du will be in terms of u. We substitute for u in there, and that's what f prime of g of x really means. First find the derivative of the outside function, then substitute the inside function in there. This also explains the name of chain rule, because if you have a composition of several functions, then you can think of this as being a chain of variables where each variable is a function of the previous, and this tells us how to differentiate the last variable in terms of the first. You just differentiate each function in the chain and then multiply them all together. So let u be 1 plus x squared and y be x power 7. Then dy over du, used by the power rule, is 7u power 6. du over dx is 0 plus 2x, so just 2x. The chain rule says then dy over du is 7u power 6 times 2x. If I substitute 1 plus x squared for u, I get 7 times 1 plus x squared to the power 6 times 2x, or written in a more usual way, 14x times 1 plus x squared to the power 6. Before we stop this example, let's look at the structure of this stage in the answer. So I have two factors. In the first factor, I have differentiated for the outside operation, which is power 7, and in the second factor, I differentiate what is inside. That is essentially what this combination of power rule and chain rule tell me. If you have power of a function, first you differentiate for the power, at which point you keep the inside as it is. Then you multiply on the outside by the derivative of what's inside the parenthesis, the function whose power is the original function. Let's use this observation to differentiate the cube root of x squared plus 1 power 5 directly. We can think of it as a composition of three functions. First x squared plus 1, then power 5, then cube root. But we can shorten our work a little bit by writing cube root of the fifth power as power 5/3. So now I differentiate for the outside function, that's power 5/3. So I get 5/3 times what is inside to the power 5/3 minus 1. Of course, that's 2/3. Now on the outside, I multiply by the derivative of what's inside the parenthesis, namely x squared plus 1. The derivative of that is 2x. So this is the derivative of the given function. Again, doing a little bit of simplification, we get 10/3 x times x squared plus 1 to the power 2/3. We will do one more example in this session. This is the derivative with respect to t of the quantity 1 over 2t minus 3 to the power 7. I can use the quotient rule, but since the exponent is a constant, I can also write it in terms of negative exponents. Power 7 in the denominator, where you have just one term, is same as in the numerator power negative 7. In fact, as we will see later using the chain rule, we can always avoid the quotient rule instead using the product rule. And what we are doing here is essentially the same thing. We couldn't do this before because we didn't have the chain rule, so we couldn't differentiate powers of an expression. Remember that the power rule also applies to negative exponents, so I can do this differentiation the same way as I did the previous example. First, differentiate for the power -7. So I get -7 times the quantity inside the parenthesis to the power -7 minus 1. -7 minus 1 is -8. Now I multiply this with the derivative of what's inside the parenthesis. Inside the parenthesis I have 2t minus 3. If I differentiate that with respect to t, I get 2. So I get -14 times the quantity 2t minus 3 to the power -8. This concludes our initial look at the chain rule.